Okay, this talk is on acidity and pH. We're going to look specifically at the question, how does concentration of an acid affect the pH of a sports drink? So any sports drink, Gatorade, Powerade that you drink actually has a certain amount of acids in it, and we're going to look specifically at citric acid throughout this unit. So just a quick review of acids and bases because it's been a while since we talked about these. There's a definition for acids. Acids always produce what's called a hydronium ion. That's going to be really important today. And here's the mechanism below. Basically, you take a water molecule, and every acid has a hydrogen in it. So, for example, hydrochloric acid, HCl, is that. And this is the part we're talking about right here. Nitric acid would be HNO3. That's another example where the hydrogen would be in this case. So those are two examples of different acids that produce a hydrogen plus ion, which reacts with the water, and as a result we get this hydronium ion. And by definition, that's what an acid is. So how do acids produce hydronium? Well, with this acid here, this is going to come over to the water molecule. It's going to interact here, and what happens is these parts split off here, just like we normally would for an ionic salt. And so if you think about how an ionic salt dissolves in water, we have this is a positive ion, and so what's surrounding it is the negative portion of a water molecule. So here's the hydrogen and the oxygen parts. The black part is negative, the red parts are hydrogen, those are positive. And so those are attracted to that part of the acid, the hydronium ion. And so that helps to dissolve it in the liquid. On the other side, the anion is going to have the opposite parts attracted to it. So I'm going to draw two different water molecules here and here. So these little red guys are the hydrogens. Those are the positive ends of the water molecule. And again, those help to dissolve the anion portion. Bases do the exact same thing, except it's the opposite. They produce hydroxide ions, which are OH. So if we are to take water H2O, so that means there's an oxygen bonded to two hydrogens. That reacts with a base. The base yields an OH, that's the hydroxide ion, here, plus the base has an H, a hydrogen plus, that's attached to the base, whatever that is. So an example of a base would be sodium NaHCO3. This is sodium bicarbonate. What happens is this sodium leaves, this hydrogen attaches to this, then we end up having H2CO3. So just a basic overall characteristic, acids produce hydronium, bases produce hydroxide. And so these guys are going to be really important when we get into towards the end of this talk today. These taste sour, these taste bitter, these feel slippery, kind of like soapy, and these react with active metals and they produce hydrogen gas. Now, we're going to talk briefly about strength versus concentration. We talked about this earlier in the year too. Just a refresher, strong acids react a lot. So for example, in this case, the number of hydronium ions, there's one here, 2, 3. So that's addressing this question. The number of acid molecules, there's only one here. So that's a strong acid. That means most of the acid has interacted. So there's 3 anions, 1, 2, 3. Now if you talk about a weak acid only has one anion. It has 1, 2, 3 acid molecules still sitting in the solution. And so that means it hasn't interacted with the water very much, therefore it's a weak acid. In this case, the weak acid only produced one hydronium ion. Concentration versus dilute. This is referring back to what I talked about in the last talk. The solute is the acid or base, where the solvent is water. Remember, solute is the smaller amount of substance, the minority. the littler part, whereas the solvent is the majority. So water is a majority of what makes up an acid solution. Now, a low concentration, pretty easy to understand. It has 1, 2, 3 solute particles. Higher concentrations might have 1, 2, 3, 4, 5, 6 solute particles. So there's more of them, twice as concentrated. So we'll go here equals times 2, which equals that. So concentration versus dilute and strong versus weak. Here's a table that summarizes that. Strong acids react a lot, weak acids don't. Concentration also plays a part. If it's concentrated, there's a lot of it. I'll put a positive sign here. If it's diluted, there is maybe less of it. Here, a negative sign. Acids and bases act as electrolytes. It's a really important part. So strong acids are strong electrolytes. Weak acids are weak electrolytes. Same with the bases. So into the last part here, this is for pH levels. pH is a scale from 1 here to 14 here, 1 being acids, 14 being bases. This is review. Now, the scale is actually logarithmic, which means we use this fancy equation to figure it out, and we'll use that today. It's really simple. I'll show you here in a second. The base for the logarithms are a base 10. So you probably remember doing this in math a little bit using the base 10 log system. The pH scale is a base 10 log system, which means we use it as a base 10, and we can do a couple different things with it. One is we can find pH. Before, we've just used like a meter to determine pH. Now we're actually going to be able to figure out how much the pH there is. And that's used by this hydronium ion. The hydronium ion, remember, comes from the acid. So the acid concentration tells us in molarity. Remember, molarity is moles per liter. So whatever that acid concentration is, we can put into here to determine the pH. So if we have a concentrated acid, we'll know that the pH is going to be lower. If it's a lower amount of, if it's concentrated base, I should say, it's going to be a higher pH. So here's just a graph showing that. The higher the concentration of the hydronium ion, the lower the pH. If the hydronium ion, as it decreases here, the pH gets larger. Now, what does the log scale mean? One important factor is that if it's a pH 4 to pH 1, then it's 1,000 times more acidic. If you go from pH 3 to pH 1, it's 100 times more acidic. And if you go from pH 2 to pH 1, then it's only 10 times more acidic. So for every step you take, it's a factor of 10. That's what the base 10 scale means, the logarithm base 10 equation means. So here's an example of calculating pH, and we'll have to do this in class. Basically, you're going to find the pH of a concentration of hydronium is 0.25 molar. So this is pretty easy. We use our equation from the previous slide here, this one, and there it is. So we take this equation, we plug 0.25 molarity into here, and then we put it into our calculator. We find out that the pH is 0.60. Now, if we want to find the concentration of the acid, we can do the same thing. From the pH is 2.7 now. So use the same equation, this. We're going to substitute 2.7 in for this pH value, plug it into our calculator, and we get the acid concentration to be 0.0020 molar. Remember molarity? Molarity is always in moles per liter. So we can kind of go back and we can find some other things out about that later on. So it's something to keep in mind. Notice I've used a different equation here than I used here. So there's two different equations that we can use. Those are two things you're going to want to be able to apply in class. That's it for the quiz, or for the video. Go on and take the quiz if you would please, and that's it for today.